You can probably see that chemists are more concerned about the heat Q in a reaction than they are the work W. In physics, you will definitely use heat and work for different kind of calculations, jazz like that. But in the chemistry world, heat is important. Now, if the heat is transferred, exo or endothermic, but if it's transferred at constant pressure, which gets the symbol Q sub P, then Q sub P, heat transferred at constant pressure, gets a special name, enthalpy. And enthalpy is delta H. And we're going to talk about enthalpy quite a bit in this class as well as in Chem 223. Earlier we saw how the overall energy of the universe equals heat plus work. You don't create or destroy any energy, and heat and work are about that. If the heat is being transferred at constant pressure, then delta E equals delta H enthalpy plus the work. But most of the time in chemistry, the work is almost zero. There's a few exceptions when it's not, but boy, by default, it's going to be equal to zero. So most of the time, that enthalpy equals the overall energy change for a reaction. So if you can calculate the energy change, the enthalpy for a reaction, you've got the overall energy change, which is pretty cool. Delta H is just like Q. If delta H is a positive number greater than zero, it's endothermic, so energy is needed to make that reaction happen. On the other hand, if delta H is a negative number less than zero, that means it's exothermic and energy is being released by the system. There are lots of different delta H's. We're going to talk about delta H VAP, delta H reaction, delta HF, and there's lots of different things. Those are all specific delta H's for a specific reason, and we'll talk about them as we need to. But all those delta H's are just enthalpy, and enthalpy is really important because most of the time, the enthalpy change of a reaction is equal to the energy change for the overall reaction, and that's kind of cool for chemists and people that study thermodynamics. This reaction is the combustion of propane. Propane is C3H8. Combustion reactions are something organic usually, plus oxygen, making CO2 and water. Notice it says that the standard molar enthalpy of combustion is minus 2044 kilojoules. And it says, is this reaction exo, endo, what need more information, et cetera, et cetera. Well, big surprise, punchline, that's a negative number, and that's an enthalpy. So if enthalpy is negative, that means that it's going to be exothermic, all right? You literally just look for the sign of delta H to see if it's exo or endo. Negative means exothermic. Positive means endothermic, so no problem. So delta H reaction is probably the most common of the delta H forms, and it's the enthalpy change for a reaction to take place. So in the lower right-hand corner there, that's hydrogen and oxygen making water. The delta H for that reaction is minus 484 kilojoules. So to make that reaction go with 2 moles of H2 and 1 mole of oxygen making 2 moles of water, you're going to get energy out. It's exothermic. You're going to get 484 kilojoules out. And by the way, a kilojoule is 1,000 joules, or 10 to the third joules is 1 kilojoule. Don't let that interrupt you or confuse you. Sometimes you'll see reactions like in the lower left right there. This is another way to write those kind of reactions. And notice that the reactants are on the top and the products are on the bottom. When you go top to bottom, those are the exothermic values. So that's another way to show exothermic. That's more of a physical chemistry kind of application of these, but if you do see it, I just want you to know. If the arrow would have been going up, that would have been endothermic. We're going to try and keep it more like the reaction there on the right. That's a true thermochemical equation. Delta H values, delta H reaction values, depend on how the reaction is written, and it also depends on the phases of your reactants and products. So let's look at this reaction, which is hydrogen gas and half of an oxygen molecule making water. And again, I don't usually like using fractions, but I'll tell you there's going to be something coming up that I have to use fractions too. Either way, this delta H is minus 242 kilojoules, so it's exothermic. And you can think about that as making 1 mole of gaseous water, you're going to get minus 242 kilojoules of energy out. However, let's say that your instructor said, you better get rid of that fraction. So you multiply everything through by 2, no problem. You can take that old delta H1, which was minus 242, and just literally multiply it by 2 to get the new delta H. So delta H for that second reaction will be twice the first one. It's going to be minus 484 kilojoules. So if you multiply a reaction by 3, you'll multiply the delta H by 3, etc., etc. But then, oops, I forgot, we're actually not making water, we're breaking water down. So we want to have water as a reactant making hydrogen and half of an oxygen. So compare this to the first one, to delta H1. The reaction is basically the opposite. We flipped reactants and products around to get this new version in green right there. So delta H3, the value of it is going to be the opposite sign of delta H1, because in delta H1 we had reactants going to products and water was being formed. In delta H3, the water gas is breaking down to H2 and 1/2 O2. So this, if you flip a reaction, you just change the sign. What was endothermic becomes exothermic, what was exothermic becomes endothermic, etc., etc. Finally, all of these reactions have used gases: H2 gas, O2 gas, water gas. Maybe you want to have a good glass of water, liquid water, no problem. But your delta H value will be different. So when you make H2 and oxygen, add oxygen to it to make liquid water, your delta H has a different value than in gaseous water was made. This particular one is minus 286 kilojoules, a little bit more exothermic than when you're just making gaseous water. These thermochemical equations are just regular chemical equations, but they have the energy part associated with it. And there are different ways to write the energy component. So what we'll do most of the time is what you're seeing in the top right there. This is methane and oxygen making CO2 and water, and the delta H value minus 802 kilojoules. However, sometimes it will be helpful to think about that minus 802 number. That's energy being released by the chemicals. So that means 802 is going to be like a product. It's something that the methane and the oxygen are releasing. So if you see 802 kilojoules as a product, that's an exothermic reaction. It's an alternate way to write how much energy is being released. On the other hand, of course, if the 802 was a reactant, then it would be a positive delta H. You need that energy to make the reaction go. So either way is fine. You can use them. Most of the time we'll use delta H equals and then negative or positive. But if you see energy as a product, that's exothermic. And likewise, energy as a reactant would be endothermic. If you think about it, though, as 802 kilojoules as a product, you can write different factors to make more sense of the reaction you're looking at. So if 802 kilojoules is a product, that means for every mole of CH4 that you burn, you're going to release 802 kilojoules of energy, which is kind of cool. And we get that because it's one CH4 making 802 kilojoules. And likewise, for every 2 moles of water that you make, you're going to get 802 kilojoules out. So you can see how this can be important to chemists. All those relationships, those stoichiometric factors, where we compared reactants to reactants, reactants to products, products to reactants, etc., etc. This is one more version of this we can do now. You can have 802 kilojoules per 1 mole of methane. You can have 802 kilojoules released per 2 moles of oxygen burned. There's lots of different kind of applications for this, which makes it pretty cool. So here's an example of a kind of application of this kind of process that might be helpful to you. It says how many kilojoules of energy are released when 128.5 grams of methane, CH4, are combusted. And there's the reaction again. Methane plus 2 oxygens makes CO2 and 2 waters, and minus 802 kilojoules is the delta H value for this reaction. So what we're going to do here is we're going to turn grams of methane into moles using the molar mass. And then we're going to use the fact that for every mole of CH4 that you burn, you're going to get minus 802 kilojoules of energy out. So what that looks like, you start with the grams of methane, turn grams of methane into moles. Methane's about 16.04 grams per mole. And then methane is part of the reaction. 1 mole of methane is in your one reaction, and 1 mole of the reaction minus 802 kilojoules. So when you multiply all those things together, you get minus 6.43 times 10 to the third kilojoules of energy out. That's the energy released for burning 128.5 grams of methane. And it's a lot of energy. And that's what we use. Natural gas is what this basically is, methane. It gives off a lot of energy, keeps our houses warm, keeps our keeps our hot water heaters going if that's what you've got. So it's a pretty cool fuel source for what it's worth. But anyway, this just shows you an example and how you can use these for your advantage. In this example, we'd like to know how many kilojoules are released when 32 grams of oxygen are combusted with methane. So this is a similar kind of problem. We're going to go grams, in this case, of oxygen to moles first, and then we'll use the conversion in the reaction to turn moles of oxygen into value of delta H. So the molar mass of oxygen is 32.00 grams per mole. So 32 grams of oxygen divided by 32.00 grams per mole is 1 mole. However, in the reaction itself, it says that there's 2 moles of oxygen burned per 802 kilojoules. Now we have 1 mole of oxygen, and there's 2 moles of oxygen for every minus 802 kilojoules. So we're going to take that 802 and divide by 2. The answer here comes out to be minus 401 kilojoules of energy. So again, grams to moles is the first part. And then 2 moles of oxygen are burned for every minus 802 kilojoules that come out, minus 401 kilojoules. Most enthalpy values, most delta H's, have a little 0 kind of next to them, or a degree symbol is a better way to think about it. And that degree symbol is standard conditions. Standard conditions means that you're at a pressure that's about an atmosphere. It's equal to a bar, and an atmosphere are almost the same thing. If you have a solution, it's 1 mole per liter. If the temperature is there, it's going to be 25 degrees Celsius most of the time. And usually the species that you're reacting with are in their standard states. So carbon standard state, the one you see most often, is graphite. Like you wouldn't use diamond because that's a lot more expensive and rare. You wouldn't use C60, stuff like that. Oxygen, you would have a gas because that's what we're used to dealing it with. We breathe it in. It wouldn't be liquid oxygen or something like that. So if you see that little degree symbol, it just means standard conditions. And these are the kind of conditions you would have under standard times. So if you did reactions, say at the North Pole where it's a lot colder, you may have different values of delta H than your delta H standard conditions number would be. Likewise, if you were on Mars or if you were in Death Valley, somewhere like that, you would have slightly different values of delta H as well. In problem set 3, there is a pretty long list of different chemicals at the back of the problem set, and there's several different columns. And the column that's important to us in problem set 3 are what's called the standard molar enthalpy of formations, delta HFs. And these are actually pretty cool. Now, how this table came to be, there's a group in the United States called the National Institute of Standards and Technology, NIST, and people sit in their offices and basements and stuff, and they figure these kind of things out all day, and they create elaborate tables of what's called a standard molar enthalpy of formation. So if you have a standard molar enthalpy of formation, that means that you're making only 1 mole of product, 1 mole of compound, and you form that compound from elements in their standard conditions. And these are the numbers that you can look up in that table. In the background of this slide, like right there, and right there, you can see some of the representative values of delta HFs, the standard molar enthalpies of formation. A lot of them are negative, but not all of them. So like C2H4 there is positive 52.3. More of them are negative than not, but there are a lot of positive ones. But you don't need to worry about that. You can look those up in the table. And again, they're in your problem set. You can also find it online. If you go to mhchem.org/thermo, you'll see the list right there. It's also in problem set 3. One thing that's not listed in the background picture, but you will see in the table, is that all the elements in their standard states will have heats of formation equal to 0. So standard states would mean graphite for carbon, but not diamond, because diamond's a lot more rare. Oxygen as a gas would be 0, but not ozone, not liquid oxygen, stuff like that. So standard elements in standard states will have delta HF values equal to 0, and that'll be important coming up. So for these next sections, if you have that table next to you, either from the problem set or from mhchem.org/thermo, might be good to go. So the question here, what would be the standard molar enthalpy of formation equation for potassium permanganate? So we don't want the value of the delta HF, we want the equation that would go along with whatever delta HF value you'd look up in the table. And again, the punchline for these kind of questions is that you can only have 1 mole of product, and all the reactants will be elements in their standard states. So this would be the heat of formation equation, the standard molar enthalpy of formation equation for potassium permanganate. Only 1 mole of product, so there's 1 KMnO4 right there. And the reactants are going to be elements in their standard states. So potassium's normal state is a solid, manganese is a solid, and oxygen is a gas. So 1 K and 1 M and 2 O2s make up 1 KMnO4. And if you look up that value in our thermodynamic table, it comes out to be minus 813.4 kilojoules per mole. So if you form KMnO4 from the elements, that's the energy you're going to get off. And you're getting it out because it's exothermic, all right? It's a negative number, which is kind of cool. KMnO4 makes a really nice purple solution. So in the lower right-hand picture there, KMnO4 solid is on the right, and it is kind of like a purple crystal. When you place it in water to make it KMnO4AQ, it's a really nice purple color. It's one of my favorite solutions. It's kind of cool looking. So here's a question you might see. Which equation below defines the standard molar enthalpy of formation, i.e. delta HF, of gaseous methanol? All right. Now, methanol is CH3OH. You want to have just 1 mole of product if it's a heat of formation reaction. So notice the answer E has a 2 right there, so that means that E is not delta HF. Delta HF, only 1 mole of product. So A through D all have 1 mole of product, but not answer E. Now, the other part, in addition to 1 mole of product, is you must have reactants as elements in their standard states, and that means no compounds. So H2O is a compound. That means D is not going to happen. In C, CO is a compound. Answer C is not right. And answer A has methane, CH4, another compound. That's not an element. Answer A is not right. So what this means is that answer B, by default, has to be the right answer. So if you look at that, it has 1 mole of product, CH3OH, and all reactants are elements in their standard states. So carbon solid would be graphite. There's a total of 4 hydrogens, so that would be 2H2. But also what's really frustrating to me is that because you are limited to 1 mole of product, you have to use fractions sometimes with these. So we would have to write, even me, I would have to write 1/2 O2 because we only want 1 oxygen atom in methanol. So we have to use fractions here. So again, because you are limited by 1 mole of product, sometimes you, and me too, will have to use fractions when writing equations. And this is the only time time, I want you to use fractions when writing equations, all right? Only with heats of formation. All other examples, we multiply that by through to get, say, answer E. But for heats of formation, it's always 1 mole of product. Elements must be reactants in their standard states. I got to deal with it. You got to have fractions. Now, to calculate the heat transfer of a reaction, you can measure it directly. You can use experimental values. Some reactions, though, are pretty difficult to measure and arguably even impossible to measure directly. So if you can't measure them directly through, say, calorimetry or something like that, you might be able to get around it using something called Hess's law. And Hess's law is a fascinating application of manipulating equations to get the reaction that you're looking for. Now, formally, this is what Hess's law says. If a process can be written as the sum of several stepwise processes, the enthalpy change of the total process equals the sum of the enthalpy changes of the various steps, which is clear as mud, i.e., even I don't hardly understand that, so don't lose any sleep about it. Let me show you how Hess's law can make a reaction much easier to calculate by using other reactions which are easier to calculate. Because Hess's law, the definition doesn't make any sense. clear as mud. All right. Let's look at some examples and stuff here to see what's happening. So here are 2 reactions. The first one is forming gaseous water. H2 plus 1/2 oxygen makes H2O, and the value for that is negative 242 kilojoules, but you can write the negative number as a product. 242 kilojoules can be a product. That's the same thing as saying exothermic. But let's say we didn't want to stop with gaseous water. We wanted to go all the way to liquid water. Well, a separate reaction, which has been studied, is gaseous water going to liquid water. That's also exothermic, but it's minus 44 kilojoules. And we would write that minus 44 kilojoules as positive 44 on the product side to show what's happening. Well, notice in these 2 reactions, water as a gas is a product in the first reaction, and water as a gas is a reactant in the second reaction. So if you add those 2 reactions together, H2O gas will cancel out because if something's on both sides, you can subtract it from both sides and it makes it go away. You end up with H2 plus 1/2 oxygen making liquid water, and the overall energy will be 242 plus 44, 286 kilojoules. So delta H for this reaction is negative. It would be minus 286 kilojoules. But what we just did here is an example of Hess's law. All right? We took those 2 reactions and combined them to give us another reaction, which was the formation of liquid water from hydrogen and oxygen. And we found out its delta H value, minus 286 kilojoules, or 286 kilojoules as a product. This is what Hess's law is all about. So most of the time in Hess's law problem, there will be some desired reaction. And for this reaction, that's this one right here. Like you want the reaction value, the delta H value, for taking the elements and making liquid water. So you can use 2 or more equations. Almost inevitably, something is going to get canceled. In this case, it's gaseous water. And when you do that, you just combine the rest of the stuff together. The energies will add up, and you're good to go. This is another example of how Hess's law can come in kind of handy. Let's say that you wanted the enthalpy value for the reaction between hydrogen and nitrogen to make ammonia. So 3H2 plus N2 making 2NH3. And you have these 2 delta H values. And the first one is the value for making hydrazine, N2H4, from hydrogen and nitrogen. It's an endothermic reaction. The second reaction there is hydrazine reacting with hydrogen to make 2 ammonias, and that value is negative. It's exothermic, minus 187.6 kilojoules. Well, you can combine these 2 reactions in order to get the desired reaction, and this is what Hess's law is all about. Now, a couple of things. First of all, notice that we don't want N2H4 in our final reaction. We want to have 3H2 and nitrogen making 2NH3. So right away, what I would consider here is you want to try to add those equations together, because N2H4 is a product here and N2H4 is a reactant there, and they're the same phase and all that kind of stuff. So when we combine them, the N2H4 will cancel out. So what we'll do is we don't want any N2H4 in our final equation, so let's just add equations 1 and 2 together. Now what I'm showing right here is all reactants and all products, and you can see it's kind of messy, but there's 2H2 and N2 plus the N2H4 and H2 of equation 2, and on the product side you have N2H4 from equation 1 plus 2NH3 from equation 2. And why this is kind of cool, people sometimes see this better, you've got N2H4 on both sides. So in math, if you had an x on both sides, you could subtract x to get rid of it. Chemists will just cancel out N2H4. And so the pieces that are left then, you've got 1 N2, but you have 2 plus 1, 3H2, and that's going to make 2 NH3. And that's really what delta H3 is going to be all about. And to get those chemicals oriented that way, we literally just added the reactions together. So in this case, we'll take minus 187.6 and add 95.4 to it. And that gets us minus 92.2 kilojoules. So this is Hess's law in action, all right? You can see how this works out. You try to want to get rid of chemicals that don't appear in your desired equation. In this case, it was simple as just adding them together. No big deal. Hess's law is great, but there's even a better way to figure out a delta H of a reaction if you know all the standard molar enthalpy of formation values. And so if you have any given reaction and you want to find its delta H of reaction, then what you can do is use this equation right here. And this is a little weird looking at first, so bear with me. This is the summation sign. It's a capital sigma, I believe, and that just means add up all of them. So you want to add up all of the heat of formation that are products and subtract from it the summation, add up all of the enthalpy of formations that are reactants. And I'll show you an example of how this means. So basically you want to add up the heats of formations of the products and subtract the heats of formations of the reactants. Now all the heats of formation are per 1 mole. So if your equation has, say, 2 moles of something, that's where N kicks in. So if you have 2 moles, you would use 2 for that. Or if you had 3 moles, you'd have 3, stuff like that. But in a nutshell, what this delta H calculation is showing is that it's all the energy that you gain minus the energy that you spend. And I'll show you this in a little bit more. So this is actually a pretty cool way to do things once you figure out how this all works. Let's say we want to find delta H reaction for this reaction, which is calcium carbonate breaking up into calcium oxide and carbon dioxide. So to figure this out, we're going to take the sum of all the heats of formation that are products, and we'll subtract from it the sum of all the heats of formation that are reactants. So for this problem, the products are calcium oxide and carbon dioxide, and the only reactant is calcium carbonate. So what we would do is in that table that's available at the end of problem set 3 or in that website I listed earlier, we would look up the delta HFs for calcium carbonate, calcium oxide, and carbon dioxide. So here's where you'd put those values. This would be the heat of formation for calcium oxide, a product, heat of formation for CO2, a product, and we'll subtract the heat of formation of our one product. Now, all of these stoichiometric coefficients in this reaction are 1, so we're not going to worry about those little n's right now because they're all just 1. Heats of formation are per mole, and we have just 1 mole, so it's no problem. So the next thing you do is you'd look up those values in the table of thermodynamics. So you can go to mhchem.org/thermo or look it up in problem set 3, whatever you want. But these are just numbers to look up. So calcium oxide apparently minus 635.1. Carbon dioxide minus 393.5, calcium carbonate minus 1206.2. Now, the only thing I sometimes see people getting confused is you want to make sure you go products minus reactants. So that's going to be essentially like adding 1206.2 kilojoules. But at the end of the day, then, this heat of reaction, positive 177.6 kilojoules. So for calcium carbonate to break down to calcium oxide and carbon dioxide, it's going to be endothermic. It's a positive delta H value. And that's kind of a cool thing to know. Now, here's a reaction where methanol is being burned in oxygen to make CO2 and water, and we want to find the delta H reaction for this one. So this will be the same thing. It's going to be the products, CO2 and 2 waters, note the 2 right there, minus reactants, CH3OH and 3 halves O2. So like before, what we're going to do is we'll look the values up in that table of thermodynamic values for delta H. But there's 2 things I want to point out. Each of those delta H of formation values is per mole, and you can see you have 2 moles of water here. So whatever delta HF for gaseous water is, you want to multiply it by 2 because there's a 2 in the reaction. Now, the other thing is that we have 3 halves O2, and if O2 had a value, you'd multiply it by 3 too. However, oxygen is an element in its standard state, and all the delta HF values for the elements in their standard state are 0. You can look it up if you don't believe me, but honestly, it is. So in this case, then, it helps to know that the water you'll multiply by 2. It helps to know that the O2 is a reactant in its standard state, so it's going to have a delta HF value of 0. So in this problem then, when you look up those values, here's the equation written out. And again, notice that there's a 2 there by the delta HF because we have 2 moles of water in the reaction. So if you don't have just 1s, that's when you use the 2s. That would be the N value, if you will, for the value in front of delta HF for water. So again, just plug and chug. There's CO2. We saw that earlier. No big deal. Here's water, but we're going to multiply it by 2. That's because in the balanced reaction, there's a 2 right there. From that, we'll subtract the reactants. Oxygen is 0. The CH3OH would be minus 201.5. So at the end of the day, your delta H value, minus 675.6 kilojoules per mole. Good to go. So burning alcohol, like methanol here, usually exothermic. It's going to have a negative number. Here's the kind of question you might see. I'd like you to find the delta H of reaction for this reaction, C2H2 plus hydrogen making C2H4. C2H2 is acetylene, C2H4 is ethene. So we're making, or ethylene as it sometimes is called. So you're basically turning acetylene into ethylene, but don't worry about that. Now, I've only given you 2 of the 3 chemical delta HF values right there. And remember, delta H will be products minus reactants. So we've got C2H4, that's the positive 52.5. And from the product, I want to subtract all the reactants. So I've got C2H2, that'll be minus 226.7, but I don't have hydrogen, all right? Hydrogen, however, is an element in its standard state. So like O2 gas, like Na solid, like xenon is a gas, et cetera, all of those are going to have delta HF values of 0. So if there isn't a value given, then that usually means it's just 0, to be totally honest. So anyway, at 52.5 minus reactants, in this case minus 226.7, gets you negative 174.2 kilojoules per mole of reaction. So that's just kind of how this works out. Usually if the delta HF isn't given, then usually it's 0, but you should check with a table to make sure, stuff like that. When it comes to the strengths of ionic and covalent bonds, this is something that scientists always wonder too. And there's a lot of energy transfer in these different things. Now, strength can mean stronger, which can be good, but strength when stronger also usually means less reactive. So sometimes a weaker bond is preferred because it's more flexible, all right? So covalent bonds are usually used in life. DNA, caffeine, all sugars, all those kind of things. Those are all covalent bonds. They're more flexible. They're not as strong as ionic bonds, but they are more flexible, and that's really important for life. So bond order and bond energies are used sometimes to tell like how strong bonds are, stuff like that. Ionic bond strength, if you want to ever calculate it through crystal lattice stuff, you use what's called a Born-Haber cycle calculation. And it's kind of a cool thing to do. It's nothing we're going to study in Chem 222, but if you want to look in the textbook, it is kind of fascinating. At the end of the day, you just need to know that ionic bonds are stronger than covalent bonds. We're going to focus more on the strengths of covalent bonds, but Born-Haber cycles are cool things that are done in inorganic chemistry circles sometimes to figure out the strengths of things. But again, we're going to focus more on covalent bonds in this quarter. Now, in Chemistry 221, we very briefly looked in Chapter 5 at this slide right here. And I talked about at the time a comparison that you can make between molecular orbital theory and Lewis structures. And we talked about at that time how, like, the triple bond there in acrylonitrile, that had a bond order of 3, while the bond order of 2 represents a double bond. And most of these bonds were single bonds, bond order 1, all right? And as a general rule of thumb, as bond order goes up, so as you go from a single bond to a double bond and a double bond to a triple bond, as bond order goes up, your bond length goes down, all right? So a triple bond is actually a lot smaller than a double bond, and double bonds are usually a lot smaller than single bonds, which is kind of cool. This was what we saw in molecular orbital theory too, but not quite the same way. So when we talk about bond order, all right, just remember this. A double bond is 2 bonds, and that's actually smaller than a single bond, but a triple bond, bond order 3, would be even smaller than a double bond. This is a question we saw last quarter too. It says, what's the carbon-oxygen bond order in formaldehyde, this structure right there? So we look for the number of bonds between the carbon and the oxygen. The carbon and the oxygen have 2 bonds between them. That's a double bond, so that would be a bond order of 2, all right? The carbon-hydrogen bonds, each of them have a single bond between them. Those would both be a bond order of 1. So bond order of 2 is what you'd see for carbon-oxygen. Bond order of 1, even though it doesn't ask for it, would be the carbon-hydrogen bonds. We talked about how as bond order goes up, the bond length goes down. So bond order 2, a bigger bond order, is shorter than bond order 1. Likewise, a bond order 3 is even smaller than a bond order 2. So bond order goes up, bond length goes down. But another thing you can do is talk about bond energy. And bond energy is proportional to bond order. So what that means is that if a bond order 1 is, say, 300 kilojoules, a bond order 2, bigger bond order, would be have even more energy, maybe 600 kilojoules. And a bond order 3 would be an even bigger number of energy yet. So repeat after me here. Bond order is proportional to bond energy. Bond order goes up, bond energy goes up, etc. But bond order is inversely proportional to bond length. So bond order goes up, bond length goes down. And that's going to be an important thing to realize. So in that picture up there of formaldehyde, once again, we have carbon-oxygen bonds and carbon-hydrogen bonds. So notice that the carbon-oxygen double bond, 745 kilojoules. That's the energy required to break that bond apart. And that's quite a bit bigger than the carbon-hydrogen single bond. That's only 414 kilojoules to break up. So bond order goes from 1 to 2 when you go from CH to CO, and the bond energy goes up quite a bit too. Now, I'd like to do the bond length thing here, but you can't compare carbon and oxygen to carbon and hydrogen. So bear with me here a little bit. But those picometers, which is what that unit is, those picometers are a unit of length, and people can measure this with x-rays and stuff like that. Down here in the lower right, I have some units that are used a lot in this section. An angstrom, which is an A with a circle on it, is 10 to the minus 10 meters. And sometimes in lengths, this is used, they'll either use angstroms or picometers, which is what they're showing up there. A picometer is 10 to the minus 12 meters. And remember that bond energies are often in kilojoules, where a kilojoule is 1,000 joules, stuff like that. Here are 3 carbon-oxygen bonds. The first one in the upper left is methanol, which has a CO single bond. The second one is carbon dioxide, which has a CO double bond. And carbon monoxide, the third one there, is a CO triple bond. Now, those values in red are angstroms, 1.410 angstroms, 1.317 angstroms, 1.194 angstroms. Here's what I want you to dig. Carbon-oxygen bond order goes from 1 to 2 to 3. It's getting bigger as you go down to the right. But also as you go down to the right, the carbon-oxygen bond length goes down. You go from 1.4 to 1.317 to 1.194. So bond order is going up, bond length is going down. And this is what you see. You have to compare the same kinds of bonds, so just carbons and oxygen, stuff like that. But it's pretty cool. And this is what people see when it comes to covalent bonds, bond length, bond strength, stuff like that. Pretty cool. This shows bond length as related to different kinds of atoms. Now, all of these are bond order of 1. Hydrogen fluoride, hydrogen chloride, hydrogen iodide. But notice how the bond length is getting bigger. Now, what's happening here is that if you remember from Chemistry 221, sizes of atoms get bigger as you go left and down. And fluorine is on the periodic table, chlorine, and chlorine is on top of iodine on the periodic table. So the atom sizes are getting bigger. Fluorine is smaller, chlorine's in the middle, iodine is the biggest one of all. And notice how the size of the bond length is getting bigger as well. So bond length definitely depends on the types of atoms, and that's why earlier I couldn't really do the bond order, bond length thing because we had carbon, oxygen, and carbon, hydrogen. But here I can show you why. Single bond order, they're all bond order 1s, but the atoms themselves are getting bigger. And that's why the bond length increases as well. So remember, sizes get bigger as you go left and down. Down is more dramatic usually than left, but that does happen both ways. Kind of a cool thing to remember. There's always going to be some optimum distance between the two atoms in a bond, all right? If it's too close, you start to have lots of repulsion. Too far away, there's not enough glue to happen. So what scientists have done is they figure out average bond enthalpies per bond. And these aren't perfect or anything because a CH in, say, methane might be different than a CH in methanol or something like that. But overall, these work pretty good. And when you don't have anything else to measure outside of these, then they work amazingly well. So in the upper right-hand corner right there, we have a whole bunch of different bond enthalpies. And those are the energies required to break the bonds in half. So C and H there at the top is 413. That's kilojoules per mole. Cc is 348 when it's a single bond, Cn 293, etc., etc. So those are for single bonds. But notice especially here the Cc single bond, and now compare that to the Cc double and the Cc triple. A Cc single bond, 348 kilojoules per mole, is a lot less than a Cc double bond, 614 kilojoules per mole. And the Cc triple bond right below that, 839 kilojoules per mole. So we're seeing bond order go up, single bond, double bond to triple bond, and the bond energy goes up. We're going from 348 to 614 to 839 kilojoules. So the more bonds you have, the more energy you have to add to break them all. That's why bond order goes up, bond energy goes up. On the other hand, bond order goes up, bond length goes down. So in the lower right-hand corner, we have an oxygen-oxygen double bond and an oxygen-oxygen single bond in hydrogen peroxide. So notice that the bond order 2 has more energy to break than the bond order 1. However, the bond order 2 is a smaller bond. The bond order 1 is a bigger bond, 121 versus 148. So again, bond order goes up, bond energy goes up, but bond length goes down. You can use these kind of bond enthalpies to calculate delta H of a reaction. And for these kind of delta H calculations, you almost always need to draw some Lewis structures. So it might be a good idea to remind yourself how a Lewis structure can be drawn and stuff like that. In this example, it's not too bad. We want to form HCl from hydrogen and chlorine. And when you draw the Lewis structures out, HH is a single bond, chlorine is a single bond, and HCl is a single bond. So when you see a question like this and it asks you to find the delta H, it's always delta H of the reaction equals bonds broken minus bonds formed. And in these kind of reactions, that means the bonds of the reactants minus bonds of the products, the bonds that you form. And here are the three values of HH, ClCl, and HCl that we'll need here in a little bit.
Hydrogen and chlorine react to form hydrogen chloride. Because the total energy of the broken bonds is less than that of the bonds formed, the overall reaction is exothermic.
Using a table like the one I just showed, you want to do bonds broken minus bonds formed. So that means reactant bonds minus product bonds. So for this one, I'm going to break an HH bond and a Cl-Cl bond, and we're going to form two HCl bonds. So mathematically, that's going to be 436 plus 242, the bonds of the reactants. I'm then going to subtract the bonds that are formed, the product bonds. I have two HCl's, and each HCl is 431. So it's like the 678 bonds broken minus 862, the bonds formed. You're going to get an overall minus 184 kilojoule value. This is an exothermic reaction. All right, you're going to get energy out upon making hydrogen chloride. So again, to do these kind of problems, you almost always need the Lewis structures, and then it's bonds broken minus bonds formed, or reactant bonds minus product bonds. Either way is fine. Okay, so that's it for Chapter 9. I really appreciate you spending your time with me as we talked about thermochemistry and how chemists think about energy, the speeds of reaction, all that kind of jazz. If you need more help and more work on some of these kind of problems, use some of the resources that are listed right there. Of course, I'm happy to help, as well as the Learning Success Center / Avid Center. Everybody's here to help you out. Okay, I appreciate you spending time with me. I hope this has been helpful, and I sure hope you're having a great day. Thanks for being here.